Hi everyone, my name is Sarah Karen and I'm presenting a work which is a collaboration with Gerard Canal and Michael Cashmore. Our work is called Task-Aware Waypoint Sampling for Planning Robots. So we're considering robots that are navigating in some physical space and need to complete some overall tasks by visiting different locations in the environment and performing activities. And in order to represent the space in which the robots are operating, we use discrete positions or configurations in the space, which we call waypoints. Waypoints are sampled from the continuous space and represent the different possible ways, positions from which activities can be performed. Now, these waypoints are what we call a probabilistic roadmap, a PRM, first suggested by Kavraki et al. In 96. And the probabilistic roadmap, the nodes are waypoints, and edges represent feasible paths between the waypoints. Now, there are in general, two approaches to waypoint selection. So typically, you approaches either iteratively sample from the entire space, or they consider each activity separately. So when you sample from the space, you just use some random sampling approach to select waypoints and form a probabilistic roadmap and try to find a plan for your task in that way. Or in the second approach, you consider the activities that can be performed in the space, represent each activity with a dedicated waypoint. You use domain knowledge to select the waypoints, and then you have a representation of the environment of the task. Now, the problem with these approaches is that they can either lead to overly complex task representations, especially if you consider each activity separately, or it can lead to plans with compromised quality, meaning that there might be an efficient solution, a more efficient solution than the one found. Now, and another thing that corresponds to all existing approaches and applies to all existing approaches is that they all support only physical constraints that are defined over the environment. So they can represent something that has to do with the physical capabilities of the robot, what and what cannot be done, etc. What we want to do here in our framework, which we call Task-Aware Waypoint Sampling, TAWS for short, is actually consists of two main contributions. So the first is that we perform a one-time computation of the connectivity graph. So instead of iteratively sampling the PRM at every planning iteration, and remember, we are selecting waypoints in order to send this representation to a task planner, so a plan for our overall task can be found. And in existing approaches, this formation of the PRM, probabilistic roadmap, happens iteratively. So each time you fail, you throw away what you already computed and you compute a new probabilistic roadmap, or you compute some probabilistic roadmap based on your domain knowledge, but you can't find a plan. It's a one-shot chance to find a plan. So our first contribution is that we perform a one-time computation of the connectivity graph, and we form a very dense PRM. We call it a DPRM. The idea is that we perform this computation and this representation captures a fine representation of the reachability information in the space. So because we have a dense PRM with many waypoints, we have, with very high probability, a way to find a plan within our DPRM. So we won't have to resample from the map. We will use this DPRM to sample from it, and all the connectivity information will be within it. The second contribution, and I think the more maybe important contribution with respect to this workshop, is the fact that we wanted a way to support arbitrarily defined user, what we call performance preferences. So things that cannot directly be represented in the map that is used for navigation, but is important for the system operator. And we will see what I mean in a minute. The idea is that TOS, our approach, combines the benefit of random sampling together with the benefit of domain knowledge. And let me say more about performance preferences. What we want to support basically is arbitrary preferences that the system operator may have about the way robots behave. So this can correspond, for example, to social norms. We have areas in the environment that we prefer robots to do not dwell in, for example, near doors or near locations where people are having conversations or workstations of people. We have noisy robots and we want to avoid the discomfort that would be caused for the humans. So we can define that via some performance preferences that associate scores to each waypoint. We can also take into account different constraints, of course, for example, safety constraints that can be imposed on the map, but we can also have some efficiency priorities. For example, we can favor operation in specific areas of a factory, such as areas where the robot would have an outlet, an electricity outlet nearby. So the idea is that we account for all these preferences in a uniform way by inducing the probabilities of sampling certain positions in the physical space. So let me show you an example. This is our factory. We have a robot here in the center, this gray rectangle, and the robot needs to visit some of the machines to pick up some tools, perform some activities in the machines. This is an example from the Robotics Logistics League, or at least an adaptation of that domain where we have a complex task that needs to be performed. And we have what we see here on the top center image, we have some description of the positions from which each machine can be accessed. So the relevant activities that can be performed in the machine are depicted by these, what we call donuts. What you see in purple are the locations for each donut, but what you see in pink are the intersections. So locations from which more than one activity can be performed. That's also part of our input that we get as a description of the locations from which tasks can be performed. And so the first phase that our approach does is we construct a dense probabilistic roadmap. So as you can see here, we have many waypoints representing the physical space, the connectivity information about the physical space. Then what we do is we take the performance preferences that were specified by the user. For example, in this case, there were areas near doorways or at doorways that the user prefers that the robot avoids if possible. And we also have near these walls, we have first aid kits. And this is a constraint. So we disallow agents or robots to be in these areas. So what we do next is we take the template information, so information about the positions from which activities can be performed, together with our preference information. We combine them together, and then we take that and we merge that with our dense PRM, and we use the scoring function that is based on the preferences and the constraints that were specified by the user and the task and the description of the activities, and we let that score induce the probability by which we sample from the dense PRM. So what our problem looks like, we have a task-aware waypoint sampling, which consists, which is a tuple, in which the components are M is a set of configurations that represents the configurations in the space from the configurations from which activities can be performed. We have a set of activities that can be performed in the space by the robot, and we have a set of performance preferences, which define the scoring function that the user associates with each configuration. Then we first generate a dense PRM, which we use to iteratively sample waypoints. So we construct a representation of the space iteratively by sampling from the DPRM and not from the map. And we change the size of the sample set depending on whether the planner failed. So if the planner times out, we know that the representation is too big and we decrease the size. If a plan is found, we increase the size in order, or if a plan, if a plan isn't found, there is no solution, or a plan was found and we still have time to improve our solution is an anytime approach. So we increase the size of the waypoints in order to improve the quality of the solution. So the idea is that the probability of sampling a specific waypoint is based on the score that is an accumulation of the preferences, the performance preferences that were specified by the user. Now, every time we sample a waypoint, another point to kind of bear in mind is every time we sample a waypoint, we reduce the probability of sampling waypoints near that location. So let me finish by telling you how we evaluated our approach. So we had two main questions when we in our empirical evaluation. First, we wanted to figure out what is the benefit of this one-time generation of a dense PRM over existing approaches that iteratively construct a DPRM or that construct a single DPRM based on domain knowledge. The second question is how or what is the best way to account for performance preferences in the waypoint selection process. And as I said, we used the automated factory scenarios, which are adaptations of those that are used in the robotics logistics league. And what we compared are three approaches: TAWS, which is our approach, task-aware waypoint sampling. We compared it against the fixed waypoint generation approach by Edelkamp et al. From 2018, where they sample a single waypoint for each activity based on domain knowledge. And the second comparison was against the pure PRM approach, what we call PPRM by Kavraki et al. From 96, where waypoints are sampled randomly from the entire space, from the map. And we embedded all approaches using ROS and the ROS plan framework with POPF temporal planner for task planning. And what we measured was the number of instances solved within the different time bounds, the quality of the first and best solutions for each time bound. Remember that a TAWS and is an anytime approach, so it could, if it had more time, it could use that time to improve its solution. And we measured computation time, so how much time it takes for a solution to be found. And as a first step, we only are evaluating the benefit of using a dense PRM. So at this point, we don't talk about performance preferences. They will come later on. We are only want, as a first step, to evaluate the benefit of decoupling the connectivity analysis from the task planning process using a single dense PRM that we generate and then reuse. So this is how our results look like. Unfortunately, or fortunately, the pure PRM approach completely failed to deal with problems of significant size. So what we see here is our approach, which is TAWS, compared against the fixed waypoint generation approach. And what we see here on the left is first a comparison of plan durations, that what is the quality of the plans that were generated by each approach. And of course, we want smaller numbers. And what you can see here is that the numbers below the graph, which represent problems where our approach did better, are outnumber the instances for which FWPG had a better performance. What we see here on the right is time to solution, how much time it took to reach each solution. So FWPG is a one-shot approach where where the PRM is based on domain knowledge. And what we can see here is that there is this two kind of cases, one where the time is very high and one where it's very low. But in any case, our solution, in the best scenario, our solution outperformed FWPG on most of the instances, and even for finding the first solution was typically much quicker than FWPG. Now, the second part of our evaluation included accounting for performance preferences. So we used two kinds of preferences. One was hard constraints, which cannot be violated. For example, as I said, near first aid kits, where we disallow robots to be in. And we also include soft preferences. So remember, this is one of our key contributions. We wanted to account for social norms, anything that the system operator may want to impose on the behavior of the robots. And since neither the FWPG or PPRM approach accounted for performance preferences, we extended both approaches to do so. And so now, in addition to measuring plan durations and time to solutions, we also measured the quality of the plan with regards to the cost that was imposed by the performance preferences. And what we can see here, again, PPRM failed to produce results for instances with meaningful size. What we see here on the left is that FWPG, in terms of performance cost, did very badly compared to TOS, which is, maintained a zero cost. And here, cost is a penalty for violating our constraints, so lower is better. And we see that our approach managed to find solutions much more effectively. And on the right here, we see that this achievement was performed without compromising the quality of the solution, which was very exciting. So to conclude, task-aware waypoint sampling, the idea is that we decouple the connectivity analysis from the task planning process. And this allows us to not only improve performance of finding a plan in general, but also allows us to account for performance preferences in an efficient way. And of course, there are many next steps that we can think about, extending this approach to more elaborate representations of the probabilities in this domain, and to extend this to other domains. We are also going to, and this is a paper that was accepted to ICAPS 2021, which we are going to present in the summer. Thank you so much for listening. I hope you have questions for us.